Good morning, everybody. Hello.
Good morning, sir.
So, are you able to see the screen?
Yes, sir.
Okay. So, in special paper, this is my first class or second? Second or what?
Second.
Okay. So, I hope you have already know a little bit about the magnetism and particularly the three types, the diamagnetic material or diamagnetism, ferromagnetism, paramagnetism, and ferromagnetism. Okay, and other than these, so many other type of magnetic material or magnetic interactions are there. That is ferromagnetic, antiferromagnetic, and superparamagnetic, spin glass, and so on. But the most important thing is for the magnetic property is the magnetic moments. Okay, so whatever may be, what is the reason to get the magnetic moment? Then that part we will discuss later. But for time being, we will consider the magnetic moment is the basic entity for which the magnetic property or magnetic interaction takes. So interaction of different magnetic moments in different orientation and different state. So the fundamental object is in magnetism is the magnetic moment. Okay, and later on we will see that the magnetism is basically quantum mechanical phenomena. Although there is some classical analog, and we are lucky enough that classically to some extent the phenomena can be explained. Okay, but basically this is a quantum mechanical phenomena or interaction. In classical electromagnetism we know that we can get the magnetic moment with a current loop. We know that if there is a closed current or loop, a current loop, then a magnetic sheet will produce, and the magnetic moment of that sheet is perpendicular to the the direction or normal to the plane of that sheet. Okay, so if ds is the area, closed area, and I is the current, and this we know the area, the direction. When we consider the area as a vector, the normal to the area is the direction of that area. Okay, normal to the plane is the direction of the area, and so d mu is equal to I into ds. Okay, I is the current and ds is the elementary area. If if, uh, if you have a closed loop, you have a closed loop. This one current is flowing in anti-clockwise direction, so right hand thumb rule. Then the direction of the magnetic sheet or magnetic moment, it will be d mu. So this should be actually d mu. This is ds, the area, and d mu equal to I into ds. So this is not ds but d mu. Direction of ds and d mu will be the same as I is a scalar. Now the area, the unit of this magnetic moment will be will be ampere into meter square. Ampere is the current and meter square is the area. Okay. And the magnetic moment d mu points normal to the plane of the loop of the current. That you have read somewhere in your BSc syllabus, and therefore we can it can therefore it can be represented either parallel or anti-parallel to the angular moment, and we will later on see that this magnetic moment will be associated with the angular moment vector. Now whatever here the current is considered for the flow of the charge or electron, and the we consider here the electron has a mass or massive particle, okay, having a mass. So you have the and charge particle, if it flows, charge particle flows means current will produce, and this current, if it is closed loop, then the current will produce the magnetic field, okay, and this magnetic field is perpendicular to the magnetic sheet, and the magnetic moment will be the perpendicular to the area of that sheet closed path, and this is due to the charge. And we know that electron has both the charge and mass, and since it is revolving in a closed path, so due to the mass will produce the angular momentum because it is revolving with respect to a with a respect to an axis, okay. So the charge will give you the magnetic moment. हाँ ये रजिस्टर भेज दीजिए. And magnetic moment and angular moment is due to angular momentum is due to the mass which is revolving around the axis, okay. So the magnetic moment is associated with the angular momentum. Now for a bigger loop, let's say we have considered for the elementary loop, closed loop, which has the elementary area ds. Now you have a bigger loop which has the area of s. Now if you imagine that the bigger loop can be divided, or within the loop you can sum up the bigger loop with the assembly of or the arrangement of smaller loops. And since the outermost circumference, it is current is flowing either the clockwise or anti-clockwise direction, so the every loop, if it is connected with the outermost circumference, then the if you for time being you consider the current is flowing clockwise direction. So you consider that I should draw the figure, but unfortunately it is not there. So you take a closed loop, a small loop within the bigger one. eh? So this is, let's say, circle. Another circle, two circles are there, three circles are there, which are which are one side is touched with the circumference. Now, if you consider the smaller one, so the current always all the loop, the direction will be the parent one. So parent one we have considered that it is clockwise. So every loop which is connected will flow in clockwise direction. We for this is itself. Okay. So now two loops, inner loops are close together. Okay, touch together, let's say. So in one left, if you consider two, then the left one at the two has touched with one another, and you consider the left one. So left one is flowing in clockwise direction. Similarly, the right one also, the current flow will be clockwise direction. At the meeting junction, so the current at the meeting point for the left loop, it is downwards direction. Tangent will be in downwards direction. Up one, the right one will be the tangent direction will be upward. So similarly, all for all the side, all the thing will be cancel out in pair. So left hand side, upper one is right side or upper one. So left and downwards and upwards will cancel out. Similarly for the next one, similarly for the top or bottom, one will be positive x direction, another will be negative x direction, will cancel out in pair. So inner, all the inner will be cancel out, only the outermost orbit, outermost circumference will persist. So we can write the, if nu is the moment for the bigger loop, then mu equal to integration of d mu, where d mu is the magnetic moment for the elementary loop, and this will be I into ds, and ds sum over ds means will be s. Okay, the area of the whole circuit or whole loop. Now the magnetic relation between the magnetic moment and the angular momentum. Now, a current loop occurs because of the motion of electrical charges, right? Right. All the charges, since we are considering, we are considering associated with particles that have mass, that I already told. So we are considering a massive a charge having the mass. So the charge will give you magnetic moment, mass will give you angular momentum, and the magnetic moment is always connected with magnetic angular momentum. Okay. So in atoms, the magnetic moment associated with the orbiting electron and along the same direction as the angular momentum L of the electron, and is proportional to it. So the magnetic moment mu will be gamma into L. L is the angular momentum vector, and from the quantum mechanics, you know that gamma is the gyromagnetic ratio, and L equal to H cross L. Okay, so now the precision. We know that if you have a magnetic field H, you place a magnetic moment, then the magnetic moment will try to orient or try to incline towards the magnetic field. So magnetic field will try to align the magnetic moment to its own direction. Okay, and now, if a magnetic moment mu is in the magnetic field A, then the energy of the magnetic moment associated with this magnetic moment will be E equal to minus mu dot H. Mu is the magnetic moment, H is the magnetic field. So the energy associated with this magnetic moment will be minus mu into H. That we know. Okay, and so that the energy is the negative sign is because the most preferred configuration is the is towards its own direction. So when the theta is minimum, hmm, 0, then the energy will be the most stable energy, and that will be minus mu into A, right? Stable, most stable configuration. So that's why the negative sign comes. The energy is minimized when the magnetic moment lies along the H direction. Now, due to this magnetic field, there will be a torque G on the magnetic moment given by G equal to mu cross H. So two things are associated. One is the energy, because magnetic field is there, magnetic moment if you place. So in this magnetic field, energy will be, potential energy will be associated with that. And that potential energy equal to minus E into H. Another thing is the torque. You have the magnetic field, you have the magnetic moment, and that magnetic moment will try to orient the that magnetic field will try to orient the magnetic moment in its own direction or whatever. So due to for the orientation, definitely torque will required. Okay, couple will requires, and couple is the represented by the torque of the couple. So now, what is the importance of this torque? How, this is because the torque is there because if for time being we don't consider the torque is not there. If the magnetic moment were not associated with so if torque is not be associated with the magnetic moment, would tend to turn the magnetic moment towards the magnetic field. So what torque will do? The magnetic uh, field will try to orient the magnetic moment towards its own direction. Okay. Another thing, torque is there, which try to resist that. Okay. And later on we will see, due to this torque, it will not orient to, or incline towards the magnetic field, but it will precede with respect to with the axis, with respect to the magnetic field. So magnetic field, if it is in z direction, so it will precede with respect to that z direction or magnetic field direction. Okay. There will be a torque G on the magnetic moment given by G equal to mu cross H, which, if the magnetic moment were not associated with any angular momentum, will tend to turn the magnetic moment towards the magnetic field. Okay. So magnetic field will orient the magnetic moment towards its own direction, but due to the presence of the torque, which is associated with the magnetic moment and angular momentum, which resist this orientation towards the magnetic field. Instead of this orientation, or instead of the align towards its own direction, it precises around the magnetic field. Okay. And since mu is associated with the angular momentum L, which is given by equation 1.3, and because torque is equal to the rate of change of angular momentum, we know that torque is the rate of change of angular momentum, and that can be written. So G equal to mu cross H and G equal to dl dt. Okay. And mu equal to gamma into L. All this thing we have already seen. So dl dt equal to mu cross H, and that is equal to, so d mu dt, this is dl dt, the L equal to mu cross L, mu equal to gamma into L. So L will be 1 by gamma into, and so d mu dt equal to gamma into mu cross H. Okay. So the rate of change of mu, that is the magnetic moment, is perpendicular both mu and H, because it is mu cross H. So d mu, direction of d mu dt, the rate of change of mu with respect to time, is not simply the shifting or the alignment of the magnetic field. Instead of that, it is a cross product both of these, mu and H. So d mu dt, the rate of change of time derivative of mu, is the direction of that will be both mu, perpendicular to mu and H. Okay. So let's say H is in the direction of z axis, mu is some let's say x axis. So in y axis the movement will be that, and that is possible when the magnetic moment mu will precise around the z axis. Okay, so direction will be make a cone, and the direction of that orientation will be perpendicular to the plane containing x and z direction. That means the direction of the precision will be of y axis. Okay, so the rate of change in mu is perpendicular both mu and h rather than turning mu towards h. So, so for this torque or vice versa, since it is not simply the orientation towards the the z direction or the direction of the magnetic field, instead of that it try to precise. Okay, and or for the presence of the torque, or the torque is developed due to this precision. So the due to this frequency, because this is rotating with respect to the z direction, the this angular frequency of this precision is called the Larmor frequency, is omega L equal to gamma into H. Okay, gamma is the gyromagnetic ratio, and omega L equal to gamma into H. Now, the Bohr magneton. So all these thing will be is the introduction or the terminology which will be used later. The Bohr magneton. The magnetic moment, we know mu equal to, if we consider this current loop, so mu equal to I into area. Okay, mu into I into area. And area, for simplicity or simple cases, it is a circle and circular disk, so pi r square, right? And that is equal to E minus E cross H minus EH cross divided by 2m. M is the mass of the electron, and that is the definition or the quantity of the Bohr magneton. So Bohr magneton is the unit to represent the magnetic moment. So mu b is the Bohr magneton defined by the quantity mu b equal to EH cross divided by 2 mu e, 2 me. And because of the negative charge of the electron, the magnetic moment is antiparallel to its angular momentum. Okay. And so mu and angular momentum L, it is considered for the electron. It is in general gamma into L. L is the angular momentum, and the if it is electron, then the angular momentum and the magnetic moment will be the antiparallel. For the other charge, let's say positive charge, then this will be the same direction, okay, parallel to each other. So magnetic moment and the angular momentum will be parallel for electron, and later on we consider most of the cases is the due to the electron. So the angular momentum and magnetic moment is antiparallel to each other. And gyromagnetic ratio of the electron is defined as gamma equal to minus E divided by 2 me. So, so omega L equal to EH gamma into H, that means uh, EH divided by 2me. Similarly, you can represent in terms of mu b in terms of so gamma into minus of gamma into H cross. Now, so these are the terminology which will be used in frequently. Now we will consider that an atom is placed in a magnetic field. Okay, so we will see what will be the is consequence. So an atom is an isolated atom is placed in a magnetic field. So the magnetic moment of an electron spin is in free space is given by mu equal to gamma H cross S. Okay. And because we are here, we are L equal to here gamma H cross L. So here we are considering only the spin. Okay. And the so mu equal to gamma H cross A minus G mu B into S. So H cross S is the spin angular momentum, right? Now an electron spin in a magnetic field H parallel to the Z direction has an energy equal to is equal to E equal to minus E cross H that we have seen, and that is equal to G mu B H dot S, right? So if you use the equation 2.1, you will get the energy equal to minus mu into H. You put the value of mu, that is minus G mu B S, that will give you G mu B H dot S. So E equal to G mu B H dot S, that is MS, okay, MS into H. Right? So G mu B H into MS. MS for the for electron system. So MS equal to plus minus half. G equal to 2. So E will be equal to plus minus mu B into H. Right? अभी क्लास ले रहा हूँ 10-15 मिनट।
नहीं ठीक है सर, वो इलेक्ट्रिक वाला जो दिए थे,
कौन सा
लिस्ट दिए थे ना, क्या क्या मंगा रहा है क्या, आप रखते थे, आपको बताया
वो लाइट फाइट का
लाइट वाला, हाँ देख लीजिए, अब जैसा कहिएगा।
ना वो लाइट का वो जो 3 बिल्डिंग के सामने
तो लगा दिया है।
हाँ तो वो लगाने का
हाँ उसको देख लीजिए, देखे कि नहीं अभी आप?
नहीं देखो
नहीं तो वो लगा के दिया है, लोगों ने रखा है, का है।
अच्छा
बहुत छोटे मतलब स्क्रीन टाइप का है, आइए देखिए। हाँ खाली वीडियो तो आइए
ठीक।
और उस लाइट का भी सामान के लिए जैसा कहिएगा। हाँ ऑर्डर करें, क्योंकि 14 तारीख लास्ट डेट है।
वो आपके पास कॉपी है ये वाला जो लिस्ट बोलते हैं इलेक्ट्रिक का? तो ठीक। So in addition to the spin angular momentum, electrons in an atom possess the orbital angular momentum also, because you have spin, you have orbital angular momentum. So if the position of now ith electron in the atom is Ri and it has the momentum Pi, an angular momentum, Pi is the momentum. So then the total orbital angular momentum is H cross L, is given by H cross L equal to Ri cross Pi. That in classical mechanics, from classical mechanics, you know that R is the position vector, Pi is the momentum. So angular momentum will be R cross P. Okay, and if you have the Z electron, so the total angular momentum H cross L will be sum over I to Z, I equal to 1 to Z, Ri Pi. Okay. Now let us consider an atom with Hamiltonian H0 given by, so Hamiltonian H0 which is not influenced, not perturbed. Okay. So initially you have the angular moment, you have the an atom that has the momentum. Hello. Holy. So given by H0 equal to I equal to 1 to Z Pi square divided by 2 Me. Okay, that is the kinetic energy plus the potential energy Vi. So we assume that H0 has known eigenstate and eigenvalues. Okay. Now we add a magnetic field H given by H equal to del cross A, where A is the magnetic vector potential. Okay. And we choose the gauge such that A is the gauge, and we choose a gauge in such a way that A of R equal to H cross R by 2. Okay. So I will start it in my next class. I will start it from here. This is the magnetic field. Hamiltonian without magnetic field, unperturbed Hamiltonian of the system of the atom is Pi square divided by 2 Me plus Vi, equation 2.3. Okay. Now we place this atom in a magnetic field. And this magnetic field is represented by A del cross A, where A is the gauge, is given by H cross R divided by 2. Okay. Hello. Hello.
Yes, sir.
So I have given you the name of the book. Hello.
No, sir.
It is, I will follow the book of Stephen Brundle. It is Oxford University
Okay, sir.
Press, the book Stephen Brundle. And in some time, maybe a little bit from Keter. Right? The most of the thing I will follow Stephen Brundle. So please give the attendance. Ahuti? Hello?
Present, sir. Yes, sir.
Abhishek?
Present, sir. Present, sir.
Okay. Others? Adi Pratap? Adi Pratap? Argha?
Present, sir.
Aritra?
Present, sir.
Bikon Rabha?
Yes, sir.
Biplab Mandal?
Yes, sir.
Vishnu?
Present, sir. Present, sir.
Gauri? 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 Jyotsna?
Present, sir.
Manjulata? Manjulata? Mohit? Mahit? Mukul? Pranab? Pranab Pandey? Samir? Samir Ranjan Sahu? Shiv Shakti?
Present, sir.
Shivans? Shivans? Saumadeep?
Yes, sir. Present.
Swagata? Swagata Banerjee? Tania Jaiswal?
Sir, Sagoto Banerjee, present.
ठीक. Okay. So bye for today. You please give me your email. Send. Probably I have already, na? Yes, I have. Whatever may be the communication, if you require, then you send me in the email MSC AKG for MSC@gmail.com. Okay.
Okay, sir.
Not in the official this one akghosh@bhu.ac, because lot of mails from the department comes and many places, so